X-ray diffraction has a bit of a paradox when it comes to the perfect sample. As mentioned before, the sample position can shift the diffraction peaks if it is off-center. Because of this, the perfect diffraction sample would have a thickness of 0. It is also helpful if the sample's rotation has perfect homogeneity so that there is no accidental oscillation in the signal intensity as it spins. The easiest way for this to be true is if the sample has a width of 0. This infers that the best sample available will be the one that is as small as can be isolated. However, the target for an X-ray diffraction experiment is at least 1 million individual signals for each peak. Scaled up from the average unit cell, this comes out to approximately 10 milligrams of crystalline solid. So you need 10 milligrams of material that occupies 0 volume in space. That is impossible, of course. Let's talk about how to get samples to behave as close to ideally as possible within the restraints of reality. A real sample should be spread out across an area roughly matching the width of the X-ray beam from the source. This width is generally going to be between 5 to 20 millimeters. Optics such as collimators and slit sets will be used to control the shape and dimensions of the beam. There is also the potential for the beam to penetrate beyond the first layer of the crystals, so it should still have some depth to allow more opportunities for diffraction, as well as prevent the sample holder from having opportunities to diffract. Depending upon the manufacturer, many XRPD sample holders will have set depths between 2 and 0.2 millimeters. This does create the potential for secondary diffraction events, where a diffracted beam is diffracted again, but there will not be coherent enough to create true measurable events. And the additional primary diffraction events will be far stronger than the noise generated by secondary events. It is ideal if the particles on the plate are appropriately sized and relatively uniform, greater than 10 micron in size if possible, and definitely greater than 1 micron in size. Nanoparticle-sized crystals can create peak broadening effects, negatively impacting the resolution. If particles are too large, over 100 micron in size, then gentle grinding with a mortar and pestle is recommended. Finally, there's a question of morphology to consider. If the crystals are plates or needles, there's a very high likelihood that the crystals will all lay flat upon the sample holders when deposited directly. This preferred orientation artificially manipulates the intensity of the peaks, exaggerating ones corresponding to the Miller indices being overrepresented and suppressing those which are underrepresented. This is generally prevented by grinding crystals to more closely resemble blocks with smaller aspect ratios, as well as dropping the sample onto a thin layer of non-diffracting oil to allow them to remain in random orientations instead of self-organizing based upon shape. Keeping all of these factors in mind allows the scientists to collect the cleanest diffractograms with the greatest resolution and degree of detail. Without these preparation phases, peak intensity generally needs to be neglected due to the number of components that may manipulate it in unknown ways.